Hi, I'm Xu Liu from University of Surrey. I will present our work, Separate What You Describe, Language-Queried Audio Source Separation, which is done in collaboration with ByteDance. Let's start at the mixture of sound sources. It contains dog bark, bird chirp, and a thunderstorm in the background. If someone is interested in bird chirps and storm sources, what can we do to separate or extract these sources? One straightforward solution is to apply a source separation method to extract each individual source component and remix them. However, this approach is time-consuming, especially for users without expert knowledge. Let's brainstorm here. Can we design a source separation system that can separate audio sources as audio sync or audio describe? Like one can say, I want to describe the sound of a bird chirping under the thunderstorm. In this work, we introduce a language-queried audio source separation, denoted as LAS. Given an audio mixture and a natural language query of the target source, LAS aims to automatically extract the target source from the mixture, where the target source is consistent with the language query. To our knowledge, this is the first work bridging audio source separation and natural language processing. Such a system could be very useful in many applications, such as automatic audio editing, multimedia content retrieval, and controllable hearable devices. Let's listen to this example again. Here is the input of an audio mixture. If you want to separate the sound sources of a bird chirping and the thunder, you can send the language query as the input, which is a bird is chirping under the thunderstorm. And here is the separated output obtained by our proposed model. As you listen, we only extract the sound we want and the background bark dogs is removed. Compared with traditional source separation methods that mainly focus on separating sounds belonging to a predefined fixed set of source classes, such as speech and music, LAS use natural language descriptions that can include auxiliary information for source separation, such as spatial and temporal relationships of sound events. LAS also provides a potential useful tool for future source separation systems, allowing users to extract desired audio sources via natural language instructions. The challenges of achieving LAS are two. First, our LAS model should understand the complexity of natural language expressions and the characterization of their relation with the sound sources. Second is to obtain the right data for this task. In our work, our contributions are two. First, we present LASNet, which is trained to jointly process acoustic and linguistic information and separate the target source described by the natural language expressions. Second, for the research of this new task, we created a dataset based on the audio caps for LAS research. Our proposed LASNet consists of two key components, a query net that takes a language query as input and outputs a query embedding, and a separation network that takes a mixture spectrogram and the query embedding as input and predicts the target source spectrogram. In the training process, we calculate the MAE loss between the estimated spectrogram and the ground truth spectrogram. In the inference stage, we use the phase of the input audio mixture to reconstruct the target source waveform. Specifically, we use a transformer-based query network is the BERT Mini, and we use its first token embedding as the language query embedding, as it can attend all the context information of the language query. As for the separation backbone, we use a residual U-net-based separation network, and the feature-wise linear modulated layer is used after each convolutional block in the separation net to bridge the separation net and the query net. We created a dataset for LAS based on the audio caps dataset. Audio caps is the largest public available dataset for audio language research, which provides one human annotated caption for each audio clip in the training set. And we can also get the sound event labels for each audio clips from DataSet. To ensure the diversity of audio clips, we first select 33 sound event tags that belongs to 5 root categories of DataSet ontology. Then, we can retrieve audio clips from audio caps if their sound event tags are all contained in these 33 sound event classes. As a result, 6,244 audio clips are retrieved around 17 hours, and each audio clip has 1 caption in audio caps. We divided these audio clips into training data and test data of 6,044 and 200 audio clips respectively. To create the audio mixtures for LAS, we first select an audio clip as the target source, and then randomly select an audio clip as the background source. Those sound event tags does not overlap with that of the target source. We mix the target source and the background source with a signal-to-noise ratio at 0 dB. The training mixtures are created on the fly using training data. To create the text mixtures, each test audio is mixed with 5 randomly selected background sources. As a result, 1,000 text mixtures are created. Each mixture has a ground truth target source and 1 language query. We denoted these test mixtures as the last test for evaluation. In practice, human descriptions of an audio source are often diverse. To evaluate the model performance under diverse language expressions, we first randomly select 50 audio clips from 200 test audio and invite 5 language experts to annotate them. Each person labels 1 description per audio clip without any hinders and restrictions. As a result, we collect an audio test subset, where each audio has 6 captions, 1 from audio caps and 5 from the annotators. Then, the corresponding 250 test audio mixtures are drawn from the last test to create a test subset mixtures, referred to the last subtest for the evaluation. As previously methods investigated separating sounds from a mixture given sound event text, we implemented a sound event text queried source separation model as a baseline system. Specifically, the baseline model is queried by a multi-hot encoding of the sound event text of the target source in the audio set. To make a fair comparison between the separation performance queried by language, descriptions, and the sound event labels, the architecture we use for the baseline model is similar to that of our proposed LASNet, except that the query network is a fully connected layer. The data mixing strategy of the baseline are same as LASNet. We denoted our baseline systems as UNet tags for further experiments. Let's look at the experimental results on the last test set. The unprocessed systems which directly use the audio mixtures in the test set for evaluation, which indicates the lower bound of the model performance. The UNet tag and the LASNet are the baseline and our proposed method, respectively. LASNet achieves the SDR improvement of 6.35 dB compared with the unprocessed systems. This proves the feasibility of LAS and the effectiveness of our proposed approach. In addition, compared with the UNet tag baseline systems, LASNet slightly outperforms the baseline in all separation metrics, which indicates that using natural language query can obtain more accurate separation results compared with that using the query of the sound event text. Let's move to the experimental results on the last subtest set. LASNet human using our collect human descriptions as queries. We average the evaluation results of 5 language queries for each target audio source. Although the human annotated descriptions we collect has a different word distribution from that in audio caps, the performance of LASNet human is only slightly lower as compared with the LASNet systems that using the language query from the audio caps dataset. In addition, LASNet human also slightly outperforms the baseline systems on SIR, SAR, and SISDR metrics. These experimental results indicate the promising generalization performance of our proposed approach. Let's look some case studies. First, let's listen to an audio mixture. Then, if we're using a natural language query from the audio caps, that is, someone is typing on the keyboard, here's the results of loss. Then, if we use our collect human descriptions, the sound of hitting the keyboard, here's the separating results of loss. And the final one is a ground truth target source for your reference. Let's look at the second case study. Here is an input audio mixture.
Random. So I've just made two methods. I haven't really created them, but this is how I'm going to deal with them. And
if we use the language query from the audio caps, that is, a motor vibrates and then revs up and down, here is the separating results of loss. If we use our collect human annotations, the engine sound of a vehicle, here is the separation results of loss. And here is a ground truth target source as for your reference. Our code, dataset, and more demos are available at our project page. Many thanks for your listening.